In this video, we will discuss applications of the second derivative. The concavity of a curve determines whether the curve opens upward or downward. It also tells us, as we move from left to right along the curve, whether the slopes of the tangent lines are increasing or decreasing. A curve is concave up if it opens upward and concave down if it opens downward. Likewise, if it is concave up if the slopes of its tangent lines are increasing, and concave down if the slopes of its tangent lines are decreasing. The book uses the terms concave upward and concave downward. These mean exactly the same things as concave up and concave down, and I learned it the other way, so I'm going with what I know. Let the function f be differentiable on an interval ab. Then the graph of f is concave up on ab if f prime is increasing on ab, and the graph of f is concave down on AB if f prime is decreasing on AB. Geometrically, a curve is concave up if it lies above its tangent lines and concave down if it lies below its tangent lines. If f double prime of x is greater than 0 for every value of x in AB, then the graph of f is concave up on AB. If f double prime of x is less than 0 for every value of x in AB, then the graph of f is concave down on AB. To determine the intervals of concavity of the graph of f, first determine the values of x for which f double prime is 0 or where f double prime is not defined, and identify the open intervals determined by these numbers. Second, determine the sign of f double prime in each interval found in step 1. To do this, compute f double prime of c, where c is any conveniently chosen test number in the interval. If f double prime of c is greater than 0, then the graph of f is concave up on that interval. If f double prime of c is less than 0, then the graph of f is concave down on that interval. Determine where the graph of the function f of x equals x cubed minus 3x squared minus 24x plus 32 is concave up and where it is concave down. The derivative of f of x is f prime of x equals 3x squared minus 6x minus 24. The second derivative of f is then f double prime of x equals 6x minus 6, which is 6 times x minus 1. If we set f double prime of x equal to 0 and solve x equals 1, this gives us intervals negative infinity to 1 and 1 to infinity. We pick values in each of these intervals. 0 and 2 will be the easiest to work with. If x equals 0, then f double prime of x equals f double prime of 0, which is 6 times 0 minus 1, which is 6 times negative 1, which is negative 6, which is less than 0. If x equals 2, f double prime of x equals f double prime of 2 equals 6 times 2 minus 1, which is 6 times 1, which is 6, which is greater than 0. Then f is concave down on negative infinity to 1 and concave up on 1 to infinity. A point on the graph of a continuous function where a point on the graph of a continuous function f where the tangent line exists and where the concavity changes is called a point of inflection or an inflection point. To find inflection points, first compute f double prime of x, then determine the numbers in the domain of f for which f double prime of x equals 0 or f double prime of x does not exist. Determine the sign of f double prime of x to the left and right of each number c found in step 2. If there is a change in the sign of f double prime of x as we move across x equals c, then the point c f of c is an inflection point of f. It is worth noting that if f of c does not exist, there is no inflection point c f of c. For example, in the graph of f of x equals 1 over x, the graph changes from concave down to concave up as we move across c equals 0. But f of 0 does not exist, so there is no inflection point. Find the point of inflection of the function f of x equals x cubed. For f of x equals x cubed, f prime of x equals 3x squared, and f double prime of x equals 6x. F double prime is continuous and is 0 if x equals 0. If x equals negative 1, then f double prime of negative 1 is 6 times negative 1, which is negative 6. If x equals 1, then f double prime of 1 is 6 times 1, which is 6, which is greater than 0. Thus, we see that f double prime of x changes sign as we move across x equals 0, so the point 0, 0 is an inflection point. Determine the intervals where the graph of the function f of x equals 1 over x squared plus 1 is concave upward and where it is concave downward, and find the inflection points of f. The first and second derivatives of f are f prime of x equals 2x over x squared plus 1 quantity squared, and f double prime of x is 2 times 3x squared minus 1 over x squared plus 1 quantity cubed, respectively. Observe that f double prime is continuous everywhere and is 0 if 3x squared minus 1 equals 0. X squared equals 1/3 implies x equals plus or minus square root of 3 over 3. The intervals formed by these values of x are negative infinity to negative square root of 3 over 3, negative square root of 3 over 3 to square root of 3 over 3, and square root of 3 over 3 to infinity. Since square root of 3 over 3 equals 0.577, we can use x equals -1, 0, and 1 to test each of the intervals. F double prime of -1 is 1/2, which is greater than 0. F double prime of 0 is -2, which is less than 0. And F double prime of 1 is again 1/2, which is greater than 0. So F is concave up on the intervals negative infinity to negative square root of 3 over 3 and square root of 3 over 3 to infinity, and concave down on the interval negative square root of 3 over 3 to square root of 3 over 3. And both inflection points, negative square root of 3 over 3, 3/4, and square root of 3 over 3, 3/4 are inflection points. The second derivative test allows us to find relative extrema without needing to test multiple values. The second derivative test: compute f prime of x and f double prime of x. Find all the critical numbers of f at which f prime of x equals 0. Compute f double prime of c for each such critical number c. If f double prime of c is less than 0, then f has a relative maximum at c. If f double prime of c is greater than 0, then f has a relative minimum at c. And if f double prime of c equals 0 or f double prime of c does not exist, the test fails. You must use the first derivative test instead. Do note that in this case, a value less than 0 implies a maximum, and a value greater than 0 implies a minimum, the opposite of what we've come to expect thus far. Maximums on smooth curves occur when the graph is concave down, and minimums occur when the graph is concave up, which respectively imply negative and positive second derivative values. Determine the relative extrema of the function f of x equals x cubed minus 3x squared minus 24x plus 32 using the second derivative test. The first and second derivatives of f of x are respectively f prime of x equals 3 times x plus 2 times x minus 4, and f double prime of x equals 6x minus 6. The critical numbers of f of x are then x equals -2 and x equals 4. If f equals -2, f double prime of -2 equals -18, which is less than 0. There is a relative maximum at x equals -2. If x equals 4, then f prime of 4 equals 18, which is greater than 0. There is a relative minimum at x equals 4.